first talk of the IEEE GRSS-APS student chapter at the University of Southern California. We have initiated the student chapter in early 2020 under the recommendation of Professor Mahta Muqaddam. This is a joint chapter associated with two technical societies of IEEE, the Geoscience Remote Sensing Society and the Antenna Propagation Society. We would like to thank Professor Muqaddam for her advising and support for that chapter. The focus of this chapter is to mainly foster the area of applied electromagnetics within USC. And today we are pleased and honored to have the first talk presented by Professor Constantine Sideris. Professor Sideris is an assistant professor of electrical and computer engineering at USC. He received the BS, MS, and PhD degrees with honors from the California Institute of Technology in 2010, 2011, and 2017, respectively. He was a visiting scholar at UC Berkeley's Wireless Research Center from 2013 to 2014. He was a postdoctoral scholar in the Department of Computing and Mathematical Sciences at Caltech from 2017 to 2018, working on integral equation methods for electromagnetics. His research interests include RF and millimeter wave integrated circuits for bioelectronics and wireless communications, applied electromagnetics, and computational electromagnetics for antenna design and silicon photonics. He was a recipient of the Air Force Young Investigator Award in 2020 and the Caltech Leadership Award in 2017. Kindly, we would like to ask you to send your questions in the chat box, and at the end of the talk, we will answer them. Professor Sideris, the floor is yours.
Thank you so much, Michelle, for the kind introduction. And I'm honored to be here as the speaker for the inaugural lecture for what I'm sure is going to be a really exciting lecture series this year. And as Michelle mentioned, I'm an assistant professor at USC. I started a little bit, whoops, the slides are delayed. I started a little bit more than 2 years ago, back in August 2018, and made the really long voyage from Caltech all the way to USC. And for those of you who are not familiar with the geography, it's really just several kilometers away. It's really not that long of a distance. And so before I get into the talk today, which is going to focus on my group's research in computational electromagnetics, I wanted to sort of introduce my group in general and our research interests, because we have quite a diverse set of interests. And so we are interested both in computational electromagnetics and optimizations, primarily for applications in RF and nanophotonic devices, of which the lecture today will focus on. However, we also have strong interests in building hardware as well. And so many of my students work on analog and RF and photonic integrated circuits with applications spanning from biosensors to wearable devices, as well as wireless communications. And so some of these photographs down here highlight some various projects that we've done in the past for many different applications. So with that, I want to jump into the introduction of the talk. And since this talk is for the Antennas and Propagation Society, I'm assuming you all know that it's going to be related to electromagnetics. And so perhaps I don't have to spend too much time motivating why electromagnetics should be important to us. But nonetheless, the beautiful thing about electromagnetics and Maxwell's equations is that it is a set of equations that describe so many different phenomena, physical phenomena that we see in our world today. Anything spanning from very low frequencies, such as radio and television, to higher frequencies, microwave used to cook your food, or RF transmissions used for wireless communication, to infrared, which is used to generate heating, to visible light, which is responsible for everything that we see in our everyday world. And it just keeps on going on, all the way up to gamma rays, which are also described by Maxwell's equations. And in fact, as most engineers would know, but perhaps the layperson might not necessarily be aware of, electromagnetics and Maxwell's equations are really the driving or the fundamental force behind most of today's technology. All of these broad examples that I'm showing you here, microwave ovens, cell phones, televisions, lasers, satellites, everything here relied on having a very fundamental understanding of electromagnetics and harnessing electromagnetic fields to be able to design all of this technology. And so now being more specific, today I'm going to talk to you about the work that we specifically do in electromagnetics, and we really focus on computational methods, both for solving Maxwell's equations numerically, but also for using our solvers to actually tie them and close the loop with optimization methods to design new devices and to automate the design of new devices that can perform to high standards, but are still robust and can work just as well, in most cases, much better than if a human had designed them manually. And so I will start with examples in RF and millimeter wave, and then I will conclude the last half of the talk by talking about recent work in silicon photonics, so in the nanophotonic space. So before we jump into specific applications and methods that we've been using and developing, I wanted to spend a little bit of time motivating why we would want to do optimization. I mentioned that we spend a lot of our time designing solvers for solving Maxwell's equations to do simulation, but then I also mentioned that a big part of our motivation for doing that is to tie it together with optimization algorithms to automate the design of new devices. So simulation is useful for determining the performance or the electromagnetic fields or some sort of specifications of an existing device. So if I have an antenna, or if I have a hybrid coupler, or if I have an inductor, spiral coil, I can put that into a simulator and I can extract useful parameters from it. But optimization can actually help us arrive at new designs. It can help us come up with completely new designs that are only guided by our desired performance parameters or desired target specifications. And so the reason of why would you want to use optimization versus why don't you just let an engineer or an electromagnetic designer do it manually is, to me, I think quite simple. The first reason is that analytical solutions only really exist for few problems. And for those of you who have taken some graduate level electromagnetics classes, you've probably seen most or all of the problems for which you can come up with analytical solutions. Anything more complicated, such as all of these devices that I'm showing you photos of here, you need to treat numerically to compute what the resulting fields would be or parameters that you're trying to extract, such as input impedance. And so therefore, the optimal design, given a desired performance, for example, if I'm trying to design this inductor, the optimal maximizing the quality factor, maximizing the inductance given an area, or if I'm trying to design this patch antenna, maybe I want to maximize the gain at a specific angle. Maybe I'm trying to maximize the radiation efficiency. So usually I know the target specifications that I have, but the optimal design given these specifications, because of the fact that I don't have design intuition or analytical solutions, is usually not very intuitive. And so the increasing performance demands of technology today necessitate these devices that we're designing to be more and more efficient, to be more optimized, and to perform better. And so therefore, we believe that optimization can fill a gap here. It can help us meet these needs and meet these demands, and also save the human designer a tremendous amount of time. So because of the fact that analytical solutions don't exist, computers can essentially be more effective at designing complicated electromagnetic structures. This is due to the fact partially that there's been a tremendous increase in both computational power in the past decade, as well as numerical methods. And furthermore, as I have mentioned several times now, since humans are using heuristic-based approaches to design antennas or other electromagnetic devices, machines can use the same heuristics. They can be programmed to do the same, to use the same methodology to design the devices for you. So let's jump into it and set the scene. So say that we're trying to design a substrate antenna. So say we're trying to design an antenna that is on a printed circuit board, for example, or on an integrated circuit, in which case the substrate might be silicon. If it's a printed circuit board, maybe it's FR4 or some sort of Rogers material. and said we want to design a planar metallic antenna. And in order to turn this into a discrete problem that we can actually pose as a math problem for an optimization setting, we need to discretize it. And so we can assign a design region, which is designated by this grid here. Let me switch it to see if I can switch it to a laser pointer. Let's see. Here we go. And then we need to divide each of these into a grid of cells, and we can designate that each cell can either be a piece of metal or it can be left open. So it's just the bare substrate. And so, for example, in this case here, we filled out the metal cells that indicate that this is just a linear dipole antenna on the surface. And so we need to specify, if we want to pose this as an optimization problem, we need to specify a target function, an objective function. What are we trying to achieve with this antenna? Because without knowing that, we can't really tell the computer to optimize an antenna for us without knowing what we want. So first we need to decide what we want, and then we need to tell the computer in a mathematical format that that's what we are trying to achieve. And so typically the parameter that most people are interested in when they're designing antennas is the gain of the antenna, which is defined as the radiation intensity at a specific solid angle in the far field divided by the input power. And so we would like to essentially, as a test problem, maximize the gain at a specific angle. Maybe it's in the broadside direction, so that would be theta phi equals 0, 0. And so in order to do this, we need to now come up with an optimization algorithm. So now that we have the objective function that we want to optimize, we need to think of, okay, how are we going to code an algorithm on the computer that can design an antenna to do this for us? And so this is a very high level. Before we zoom in even further into the optimization algorithm that we're going to use, or the simulation algorithm, this is sort of like a bird's eye view of a block level flowchart diagram of what needs to go on. We need to pick an initial solution. This could be as simple as setting all of the cells to being empty except for the driving source of the antenna. It could be starting with a dipole antenna, a loop antenna, or some design that you know might already have good performance. And so it could be a completely random solution. And so in general, there are many viable strategies for picking an initial solution. Afterwards, we need to simulate the solution and extract performance metrics. In this case, it would be the gain of the antenna, but it could also be the radiation efficiency, it could be the input impedance, it could be a number of parameters depending on what we're interested in. And then we check, is the performance that we want met? If so, maybe we got really lucky with the initial solution, then we don't even need to do any optimization. We can just, quit while we're ahead, send a design for fabrication and call it a day. If not, then we need to use an optimization algorithm and based on the current design, figure out an adjustment to make to the design and then loop back and simulate it again and keep on going in this loop, hopefully improving the performance at each iteration until we get to a design that meets our desired performance metrics. When it comes to electromagnetic design, this is the rate limiting step. Electromagnetic simulation, as those of you who are practitioners in this field are likely well aware of, tends to be very slow, especially when you have large devices that you're trying to simulate. And it's especially becomes even more of a problem when you're in the nanophotonics regime and your wavelengths are really small and you have devices that span many, many wavelengths. But even for antennas where you may have very small and intricate features or passive devices where you need to discretize very finely to represent these features accurately, the electromagnetic simulation step can take quite a bit of time. And this optimizer step, while it's fast once you get here, it may often require hundreds, perhaps even thousands of iterations to converge. And so now if you think about the fact that an EM simulation might take you on the order of an hour, and this might take you 1,000 iterations, that means for a single starting point to get a single potential device, it might take you 1,000 hours to get there, which is really slow. And perhaps you might have the time to wait for it. Perhaps you can throw it at a cluster. Perhaps you can throw it at on a cloud cluster or something. And so one approach is to throw more computing power at it. But the approaches that we try to use in my group are to come up with simulation approaches or approximate methods that can really speed up the simulation step so that we can perform the whole optimization with a modest amount of computing power in a short amount of time. So before we get into one approach for metallic antennas that we have designed, which can really speed up the electromagnetic stimulation step for the antennas, and then we'll show you applications of that. I wanted to quickly review Maxwell's equations at a very sort of high level. So these are the differential form of Maxwell's equations. We have the curl equations here. We just have the curl equations present because that's all we need for this review. And the epsilon and the mu represent the dielectric and magnetic permeability, electric and magnetic permeabilities of the system. The sigma represents the material conductivity. For example, it could be, if it's doped silicon, it could be a lossy material. So sigma might be non-zero. And so the J represents electric current excitation. So for example, if I have an excitation of an antenna, if I have a source, that could be represented with this J. And one interesting thing to note that will become important in a couple minutes, and is the whole purpose of this brief review, is that for an electrical conductor, if you have a perfect metal, which is, I'm going to abbreviate from here out as PEC, or perfect electrical conductor, the sigma, or the conductivity, tends to infinity. So it means that it is perfectly conductive, so it has infinite conductivity, or the resistance, conversely, the resistivity is zero. And so that means that in order for these fields to be zero, the limit for the sigma, as the sigma approaches infinity, the E needs to approach zero, right? So this tells us, gives us some information that perhaps you might already know, is that the tangential electric field over a piece of perfect metal is zero. And so for a non-perfect metal, it's very close to zero. It might not be identically zero, but for a PEC, it's, if you have a tangential field as being zero and you have a non-zero current on it, that implies that it is a piece of metal. It goes both ways by uniqueness of Maxwell's equations. What that means, for example, is that this loop antenna that I've drawn here with this current source driving it, if I find an equivalent situation where I replace these metals here with currents, just currents, J's, that will create electric fields over this whole loop that have the tangential components as being zero, I will have exactly the same fields radiated and the same fields throughout the whole system. So the two systems would be identical, which is sort of like a current equivalence sort of theorem. It allows me to replace a metallic component, a PEC, with an equivalent current source instead that would generate the same fields. Of course, it doesn't say how you find that equivalent current source, but if you could find it, it allows you to make that substitution. So ideally, if we want to simulate something quickly, you might think, okay, if we have this sort of space where we're trying to simulate an antenna, what if we could just pre-compute a bunch of initial simulations? So if we have n different squares, this would require n simulations, and we could just pre-compute just one square being a piece of metal at a time. We can do this completely in parallel. You don't need any sort of information from one simulation to another. And perhaps we could take these simulations, take the fields resulting from them, add them all together. So for example, this antenna has 10 of these squares filled in with pieces of metal. So we can, from our library of all of the possible squares, one at a time being a piece of metal with the other ones being empty, we can choose the right ones and sum them together. And the question is, could we actually, would this be true? Could we get the same electromagnetic field by doing that? And unfortunately, the answer is no. And the reason for that is that superposition does not hold for metals or dielectrics. The intuitive or physical reason behind that is that metals scatter from each other. So if I have two pieces of metal here, then and I have an incident field, for example, generated by the source right here, this piece of metal will scatter the fields from this source, and then the scattered fields will get scattered, reflect off of this piece of metal, and there'll be an interaction between them. If I had just simulated the pieces of metal one at a time, then it would not capture the other piece of metal being present, and it would not capture that multiple scattering between those two pieces of metal. So unfortunately, what I propose doing here, which would be awesome because we could just pre-compute all of these, and then we could compute any arbitrary, notice that if there are n squares, there are 2 to the power of n possible antenna designs that we can design here, but we would only need to do n simulations in parallel beforehand, and we would be able to compute any possible antenna in the design space, even though it's an exponential number of them. However, we can't do that. On the other hand, if we look at current sources, these J's, they're linear with respect to Maxwell's equations. If you go back here, the J is linear with respect to Maxwell's equations. If I multiply J by something, the E's will all change. And if I have two J's, I can take the two J's separately, find the E and H from them, and then add them together, and it would be the same as if the two J's are there. What that means is that currents don't scatter from each other. They're transparent. And so that brings us to an idea. What if we can solve, instead of for a piece of metal for each of, to make our library for each of these cells, we will solve for a current excitation in each of these cells. And now let's see if we can develop, by having that library of current excitations, an arbitrary metallic structure from that. So if we start from an empty grid of cells and we just have our source current in the center, this is our source excitation. And so I've highlighted this with a sort of gradient type thing to indicate that these fields aren't zero here. The source is generating some non-zero electromagnetic fields. And so if we want to create, say, pieces of metal where I have the arrows here, here, and here, what I can do is I can find J's, currents, co-located with these pieces of metal, such that the electric fields that these three currents produce, summed with the electric fields produced by this excitation source here, create zero tangential field over these regions where I want a piece of metal. And if I find that, because it creates a zero tangential electric field over that piece of metal, over that grid, it is the same as if I had made a simulation with three pieces of metal there and the source here without any of these J's. And so the way that I find this now is that I can simulate the effect of having any of these J's one at a time and getting the fields over the whole surface. And then, as I mentioned, I can combine linearly these three J's and find the coefficients for 1, 2, 3 of these J's such that it satisfies the conditions that I get 1, 2, 3, 0 electric fields in these regions. So I have three unknowns that I need to find, namely the J's in these regions, and I have three electric field components that I need to set to 0, which is where I want these pieces of metal co-located with these J's. And so therefore, I have three equations, three unknowns. I can create a very small matrix system and solve that, and then be able to get the result of if these were pieces of metal. So now I can simulate any arbitrary antenna structure by solving a very small system of equations once I've pre-computed this numerical Green's function data that maps from a surface current to the surface tangential electric field. And so the really cool thing about this is that once you've pre-computed this data, which again can be done, is embarrassingly parallel. It doesn't need any communication. You just need to solve these simulations for the J in each cell to the electric fields mapped to these cells. Then to solve any antenna from this data to get the results of it, you just need to invert a very small system of equations. And this takes milliseconds on a personal computer, on a single core. It's super fast. And so now I want to actually show this in action in and do a little case study of a antenna that we use to design and using this methodology and that we fabricated and measured. And so before I jump into the details of that, I wanted to quickly motivate the point of why we chose this application. And so wireline communication is extremely important. People these days tend to think primarily about wireless communications, but what many people perhaps don't realize is that typically the wireless link starts and ends between your cell phone and the base station tower. Afterwards, everything else is carried along wireline links. And so when cell phone demands and wireless technology, the performance demands increase on that, that likewise increases the required performance demands on wireline communication. Furthermore, if you have a huge rack of servers, for example, companies with cloud computing such as Google or Amazon or Facebook, the list goes on, then you need to have very fast interconnects that can allow the servers to communicate amongst each other. And these days, actually, more than 50% of the energy is lost to heat in this interconnect rather than computing, which is obviously undesirable. And so as a alternative technology, many people have been looking into using optical fibers and using light instead of electricity, instead of copper wireline to do their wireline links. But the problem with optical links besides the fact they solve the bandwidth problem, so you can go really high bandwidth, but the problem is that integrated optics traditionally has been very costly and challenging, and this is changing with new silicon photonics technology these days. However, it's still not as easy as a standard electrical CMOS chip, and it's difficult to merge optical blocks with CMOS. You need multiple dies typically, and it also may not scale very well with standard CMOS technologies. So as an alternative, we have proposed looking into, and this has been a hot area for several years now, with both industry and academia looking into it, using plastic waveguides as an alternative communication medium. So plastic waveguides can be made of very cheap material. They can be 3D printed. They are typically either made of high density polyethylene or polystyrene. And in the sub-terahertz frequencies, so going down to as low as 10 gigahertz, but going up to multiple hundreds of gigahertz, they have very low propagation loss in their fundamental mode. And the main advantage is that you can couple to them using a metallic antenna. So you don't need to actually send light into them using visible or infrared light. You can actually couple energy into them using a standard metal-based antenna. And so they're more efficient than copper wireline because you don't have metallic heating through the plastic waveguide. They're not quite as efficient as optical interconnects. However, for short distances around 1 to 10 meters, which fit many of these applications that I just mentioned, they can actually, the overall system efficiency can be higher than an optical link due to the fact that you don't need to convert from the electrical domain into the optical domain and then go back from the optical domain to the electrical domain. One challenge present when trying to design such a system is coupling energy efficiently from your electrical domain, from your PCB or your chip into this waveguide, and conversely coupling it back out. Ideally, you want to couple from the surface of the waveguide, so you can just sit it on top of your PCB like we're showing here, and be able to just have the energy flow into the waveguide and then have another PCB on the other side and have it flow out into the coupler on the other end. However, the problem is, if you have, for example, a simple dipole antenna, the coupling efficiency into the right direction of the fundamental mode is only about 10%. The reason is a lot of the energy will radiate into free space. It is an antenna after all. Some of the energy will get into the waveguide, but will radiate back out on the bottom side. And some will just go in the backwards direction and not in the right direction that you want. And so our idea here was, can we design a optimized metallic structure on the surface of the waveguide in order to maximize the coupling efficiency and thereby maximize the system efficiency for this type of system. And so we came up with a heuristic-based optimization algorithm approach for this. And so we start with an initial solution, and it could be completely empty, as you'll see in the next animation that I have. We pick a random cell, and we flip that cell. If it improves our efficiency, then we keep the change, and then try another cell and keep on flipping it. If it doesn't improve our efficiency, then we check if there are any other cells that we can possibly flip that we haven't tried yet. If not, then we're done because there's nothing else that we can do. The algorithm has so-called stagnated. But if so, then we flip that cell back because it was a bad decision, and then we try another cell to randomly flip. So we call this random coordinate ascent because it is similar to gradient ascent, except we're only flipping one cell at a time, so we're only looking at one coordinate at a time. This is an animation that shows it in action. On the left is the coupler design, and on the right is the coupling efficiency. See if I can get this to play. There we go. So you can see symmetry is enforced because we expect the fundamental mode that we're coupling into is symmetric. So we expect that the optimal coupling structure should be symmetric as well. And as you can see, it starts at about the efficiency of a dipole antenna, even less than 10%, and it ends up at about 34% efficient. And so in subsequent designs, we've exceeded even 60% coupling efficiency. And keep in mind that the overall system efficiency is the efficiency of the coupler squared times the loss of the waveguide as well. So if this is, even if this is only 3 times more efficient than a dipole antenna, it is actually 9 times more efficient in the overall system efficiency because you need 2 of these antennas for the TX and the RX. So we actually went ahead and we fabricated the best design that we optimized. And we 3D printed it. And so the reason that we made this so small actually for our testing was so that we can probe it on a probe station and get the network parameters and compare to our simulations. And so you can see here, this is an actual photograph next to a US penny. And this is a 3D rendering of that. And so these are the S parameters. With overlaid, the dotted lines are the simulation results using ANSYS HFSS. And you can't really tell much from here because nothing was optimized for 50 ohms. But what you can do is you can extract the maximum available power gain, which is the coupling efficiency that we optimized for. And you can see that the simulation result matches quite closely with the measured result. And this is the system efficiency. It's not the coupler efficiency. So this is showing that it's about 13%, 13.5% or so, which is the end-to-end system efficiency. The other thing that we later noticed was that if we simulate the plastic as lossless in our simulator, the actual system efficiency jumps to 45%, which means that the coupler efficiency itself was closer to about 70%. And most of the loss in our experiment was due to this proprietary plastic that we had to use due to the 3D printer. And so in the future, if we use a better plastic that has significantly less loss, then we should be able to significantly push the efficiency even further of this type of system. So another example of using this type of algorithm, the random coordinate ascent, tied to the fast antenna evaluation algorithm, is to design substrate antennas. So for example, here we have an antenna on a silicon chip structure with a frequency of 100 gigahertz. The chip dimensions are 2 lambda by 2 lambda, so 2 wavelengths by 2 wavelengths by quarter wavelength with a ground plane on the bottom. And we're trying to maximize the gain in the broadside direction, so directly up. So we have a lossy substrate that's 10 Siemens per meter. This is typical for a bulk CMOS process, and the dielectric constant is silicon. So let me see. See if I can get this animation to work. If I can, I'm gonna have to skip it, but. Okay, well, unfortunately I can't get this animation to work, but if there's time at the end, I'll see if I can get it to work. So this is the end result. And so this is what the end antenna looks like, which is you would see it sort of forming this antenna and pixelated. And it takes less than a few minutes to come up with this design. And again, it's because each antenna evaluation takes milliseconds after you pre-compute everything. And we're driving this from here and here. And you can see that the result between using two different selection mechanisms, one of them we use completely random choice and over the whole area, sort of uniform distribution. The other one, we used another approach where we seeded the random distribution based on where we expect the optimal solution to be, which is based on another algorithm that I had to skip over today. Unfortunately, I don't have time in this talk to present that. However, you can see that the end result is very similar, implying that this is potentially close to a globally optimal solution. However, the more advanced algorithm for choosing the cells to flip converges in about 5 times fewer iterations. Let's see if this video works. It does not. I don't know why my videos are not working. At the end, what I will do, if there's time, there's interest, I will get out of the presenter view and I'll just click play on the videos. So we also came up with a cleanup algorithm, which essentially its goal is to remove cells one at a time while mitigating the effect on the performance. So the idea is that it removes cells and tries to clean up this antenna as much as possible to simplify it while not losing much in terms of the performance. And if you could see this animation, which I will come back to at the end of the talk, you would see that the end result looks like just a dipole antenna with a couple reflectors, basically an antenna that a human would have been would look like an antenna that perhaps a human designed. So when you look at this with all of these different arches and these holes and things, you probably don't think that this was designed by a human or somebody that perhaps knew what they were doing. You think it's sort of a weird looking design. However, the end result of this, which I will hopefully be able to show you at the end of the talk, shows that you end up, the cleanup algorithm actually works quite effectively for simplifying the result. And the gain loss, the performance loss is very, very modest. Okay, so jumping into the last part of the talk, and I'm running really late on time, so I'm gonna have to perhaps skip some things towards the end, is the moving to silicon photonics. So we're scaling up, moving up in frequency. Everything that we did so far was relatively high frequency. The coupler was at 10 gigahertz. The antenna was at 100 gigahertz. So now we're moving into hundreds of terahertz. We're moving to the regime where we talk about wavelength rather than frequency because the frequency is so high. So silicon photonics, for those of you that may not be familiar with it, is a very exciting field because it enables the interaction of light with electronics. Optical components can be integrated on the same chips as electrical circuits. And the cool thing about it is that you can use silicon on standard CMOS SOI processes. You can use essentially the same silicon on insulator fabrication processes for building these optical devices and waveguides at near IR wavelengths. And so the reason that there's a lot of interest and excitement about silicon photonics is that it enables many applications across a very broad spectrum, ranging from the most traditional application, which is optical interconnects, as I touched on earlier, to biosensors. You can create very sensitive resonators and use them to do biodetection for different cells, proteins, and so on and so forth, to LiDAR, so for self-driving car applications, to silicon photonic phased arrays, which can be used to design lensless cameras, for instance. So one issue that we're tackling, being computationally minded with respect to silicon photonics is that it's extremely challenging to accurately simulate them. The reason is that they span tens to possibly hundreds of wavelengths. They have feature sizes that are smaller than a wavelength, and keep in mind the wavelength is very small. Furthermore, in order to have an accurate simulation, you need to take into account all of these layers, and this buried oxide and silicon substrate layers typically are much, much thicker than this top layer, so you need to mesh and have a ton of different unknowns. And this typically makes finite element methods almost completely impractical. So silicon photonics practitioners today almost always use a tool called Lumerical or an open source tool called MEEP, which are finite difference time domain solvers. And while these tools are great and they have spearheaded a lot of excellent silicon photonic designs, the problems lie not in the tools themselves, but in the method. So finite difference time domain is very general and can be used to do many different things. However, it's in the time domain, so it often suffers from very slow convergence because you need to wait for the fields to decay. And so especially if you have a high quality factor resonator, the convergence can be extremely slow. It also has very bad numerical dispersion. So if I have a long waveguide, then the numerical dispersion, if eventually you're going to get an answer that's completely wrong if you're trying to evaluate the fields far away from it. And furthermore, finite differences lead to poor accuracy. Basically, if you do everything right and you use a central differences, which is pretty much what everybody these days does, you will get second order convergence at best. And if you have corners or sharp features or changes, or you have non-uniform gridding, that often drops even to just first order convergence with respect to your mesh size. So instead, we've looked into using a different approach for solving Maxwell's equations for these devices. So going back to the frequency domain, but using integral equations. And the beauty of integral equations is that they allow you to mesh surfaces rather than volumes, which takes the number of unknowns from order n cubed, if n is, for example, the side length of your problem, to order n squared. And so this significantly reduces the problem size. It's in the frequency domain. And because of the fact of the way the integral equations are set up, that you're computing integrals rather than doing local differentiation, you actually end up with a system that is essentially dispersion-free. And you end up with a small system of equations that can, if it's small enough, either be factored directly using something like LU decomposition, or if it's a larger system, for example, for 3D methods, as we'll touch on at the end, you can use iterative approaches such as Krylov subspace methods for solving these systems. Furthermore, we take a Nystrom approach, which allows us to achieve a high order of numerical convergence. And as a testament to that, if you just discretize as coarsely as lambda over 5 points per wavelength, so just basically 5 points per wavelength, we get more accuracy in our resulting field solutions than the state-of-the-art commercial Fdtd solver at 10 times the meshing resolution. So as a quick sort of introduction to the difference between a volumetric approach such as Fdtd or finite element methods, This is a volumetric approach. So say I have a problem where I have some dielectric medium that might scatter something immersed in another medium. A volumetric approach proceeds by just discretizing and approximating the differential equations in the differential equation, Maxwell's equations of the differential equation form. And so you approximate, for example, for a finite difference method, you approximate the derivatives both in space and time using finite differences, and then you get a discretized system that you discretize on a set of nodes, and then you get a system of equations, or if it's a time domain method, you get an iterative approach where you iterate between updating your electric and your magnetic fields. And the main point that I want to make here is that it's a volumetric method. I need to mesh the whole volume, including all of this free space around it. On the other hand, integral equation methods are a more advanced approach which leverage the surface equivalence theorem of Maxwell's equations. And I don't have time to go into depth in terms of the under the hood, how this works or the mathematics behind it. But really quickly, if you have this system here, the surface equivalence theorem tells you that you can replace it by two equivalent systems. One system that I can replace it with at the top is I can remove this epsilon2 mu2 and I can just replace it with the same material as the outside, epsilon1 mu1, and zero the fields here. And then I can find a fictitious current and magnetic and electric current density on the surface J and M, which makes it such that the fields on the outside, E1, H1, are the same as its original problem. Conversely, what the surface equivalence theorem tells me is that I can, if I flip J and M and I do negative J and negative M, then I can take the outside medium to be the same as the inside medium, set the fields on the outside to be zero, and then the fields on the inside are the same identical fields that they were here. So the reason that it's important to do this is now these two problems here, these problems where I've added these fictitious currents, they have a single medium, they're homogeneous, which means that I can use the free space Green's function for each of these mediums to compute the fields due to these J and M's anywhere in the space. And so what I can do is I can set up these integral equations we have in the top left here to compute the fields from J and M based on this epsilon1 u1 medium. I can set it here based on this minus J and this minus M to compute the fields in this space due to this epsilon2 mu2. And then I can set it equal to each other if I approach a point on the surface. And then I can solve for what J and M are on that point. I can solve for J and M by setting up a system of equations along the surface and solving for that J and M. And then based on that, I found this current on the surface, and having these current densities now allows me to plug it back into here and calculate the fields either using this problem or this problem everywhere in space, whether it's inside or outside of the medium. So this is like a very quick sketch of an explanation of how integral equations lets you just mesh the boundaries between different dielectric volumes. I don't have to mesh anything on the inside or the outside. If I have two different dielectric objects, I don't have to mesh any of the free space between them. I only need to mesh their boundaries or their surfaces. And so to not bore you too much with the equations and the theory behind it, I'm going to jump into an example. And so say we want to optimize a grading coupler. A grading coupler is like an input-output port for silicon photonic chips. It allows, as I showed here in the 3D view, an optical fiber to shine light into the chip. The grating scatters the light because of these teeth. And the idea is that you design this grating such that the light scattering coherently adds up into the fundamental mode and couples into this on-chip waveguide. Conversely, by reciprocity, if you have light coming in this direction from the waveguide, it will scatter out and couple efficiently if it's a good grading coupler into the fiber. So we want to use optimization to design a grating that can efficiently couple light from this optical fiber into this on-chip waveguide. And so the optimization parameters, the objective function is the efficiency, of course. It's power inside the guide over the incident power from the fiber. And the unknowns that we want to optimize are these grading widths. And so one way that you could do it is you could use a local optimization method where you basically have your objective function and you get the gradient to do gradient descent, which I'm sure many of you are familiar with. And so basically the idea is that I can perturb each tooth by a little bit, compute the resulting fields, and compute the sensitivity of the objective function to that perturbation. That allows me to get the gradient if I do it for all of these teeth, and then I can take a direction opposing that gradient in order to maximize or minimize that function depending on what I'm trying to do. The unfortunate aspect of this is that if I'm using this approach where I'm perturbing each tooth one at a time, it means that I need to compute n extra simulations if I have n teeth. I need to do the first simulation where I haven't perturbed anything, and then I need to perturb each tooth one at a time and simulate the result. And so if I have 100 teeth or 100 parameters, for example, that's going to take me 101 simulations per optimization iteration. And so if I have 100 optimization iterations and 101 simulations, you can do the math and realize that that's a huge amount of simulations to do the whole optimization. And so the integral equation method that we mentioned is quite fast. However, it's still, we should still do something about this fact, because that speed of that is going to quickly be overcome by the number of parameters that we have that we're trying to optimize. And so there's a well-known approach called the Adjoint Approach. And I have the math on the slide, and I'm not going to go through it because I can see that I'm like running out of time. We started 10 minutes late, so I have about 10 more minutes or so, I'm guessing. Or 14 more minutes. So I'm not going to go through all of the details here, but it is very similar in spirit to backwards differentiation. It is backwards differentiation. It's very similar, if anyone is familiar with machine learning, to backwards propagation. It has its origins in computational fluid dynamics. So it was discovered many, many years ago, and it has percolated its way through into electromagnetics and computational electromagnetics. And so a lot of recent work in designing and doing optimization leverages the adjoint method. And so what the adjoint method lets you do, it's a clever application of the chain rule. As you can see, this line that I'm highlighting with the laser pointer here highlights that if you change a grouping between taking the inverse of the system here with grouping it here and doing this operation first, which doesn't depend on your parameters, then you can save a tremendous amount of simulation time. And so, in long story short, in a nutshell, what the adjoint approach lets you do is no matter how many extra simulations, no matter how many extra parameters you have, I can have 1,000 optimization parameters. At each optimization step, I just need to run 2 simulations. My standard forward simulation, which was just the grading coupler in the state that it's currently in, and the adjoint simulation, which is the transpose of the matrix that you would get. It's the adjoint of the system that you would get from discretizing the forward problem. So I just need to do 2 electromagnetic simulations, and I can get the full gradient. Exactly, it's not a point approximation. I can get the full gradient of the objective function with respect to the parameters. And so this is a groundbreaking sort of discovery, which thanks to the CFD people, and has been also what's made backprop for huge neural networks possible, for training huge neural networks efficiently possible, because instead of having to do hundreds of extra simulations if you have hundreds of parameters, you only need to do 1 extra simulation, and you get the same information that you need to update your your parameters to try to maximize your objective function. And so one example that we wanted to do, we wanted to start with a grading coupler that would be really difficult or perhaps even impossible for a human designer to come up with on their own. And so to do that, we complicated the objective function. And instead of optimizing for a single frequency or a single wavelength, we wanted to come up with a grading coupler that, depending on the wavelength, it would couple light efficiently into different directions. And so you can see here, we took the 2 common telecom bandwidths, and based on coming in from the same optical fiber, if you have 1.3 micrometers, it couples efficiently to the right and almost nothing goes to the left direction, to the waveguide extending to the left. And at 1.55 micrometers, you have the opposite. And so this would be something that would be really difficult for a human designer to come up with, because if you had 1 frequency, you could say, okay, maybe the human can start tweaking stuff or come up with an approximate expression with a uniform grading and then tweak some things, run some simulations. But now if you're trying to do multi-objective design, this gets significantly more challenging. And so this is why an optimization approach is very well suited to tackle difficult problems or challenging problems like this. So then we ran a frequency sweep simulation. And so you can see here, this is the coupling efficiency on the right port of the on-chip waveguide, on the left port. And you can see that it peaks for the left at 1.55 as we had designed, and it peaks on the right at 1.3, again, as we had designed. This one, we actually went ahead and we fabricated it, and we've just measured it, and we have a publication in preparation. So hopefully that will be submitted, and fingers crossed it will be hopefully out soon, showing the measured results for this grading. The simulation method and the optimization methods, those have been published. So you can, if you want to learn more about all the low-level details and all the mathematics behind that, you can, that's all in the paper on these methods that we have. So as another example, we designed a 1.55 micrometer optical splitter that couples light coming in on this on-chip waveguide. It splits it into two directions. This is a SCM micrograph, how we fabricated it in-house. This is a view of the parametrization, showing the curves for showing how we used spline curves to parameterize this. And hopefully this this animation will work. If it doesn't, I'm just going to exit out of this view and just show you guys. This shows the absolute value of the fields of the starting design. So this is before we did any optimization. This was the initial design that we picked, and we told the optimization algorithm that we want to maximize the output power, making it into the two outputs. As you can see here, the two outputs, it looks like there's kind of some multi-mode thing going on. There's a lot of energy leaking into the oxide in the center. This is not a good coupler. It's less than 30% efficient. So how do we get this to work? Oh, maybe if I get out of the laser pointer. Let's see. There we go. So this is an animation showing the optimization in action. So you can see the optimization algorithm is perturbing the spline curves and is achieving a different final structure. You can see here, this is just evanescent leakage. This final result is almost 100% efficient. It was like 99.2 or 99.4% efficient in terms of all of the energy coming into the single port being split evenly into these two output ports. And so you can see that this is a time domain perspective of this. So nothing has started yet, but there's a packet of energy. This is from a time domain solver coming in. It splits, there's multi-mode interference, and then it couples efficiently into the two outputs. The other exciting thing about approaching design this way is that we spent all of our time and effort designing the algorithm to design this device, not designing the specific device itself. The specific device took on the order of minutes to optimize once we had the code to do it, which means we can change a few parameters and get a brand new device that does something else. For example, this is a coupler that does a 75-25 ratio split with light coming in. This is another coupler which does a 90%, 10% split of the powers, the input power coming in. So these are sort of the real parts and imaginary parts of the fields in terms of before and after the optimization. So this is the initial solution that we gave the optimization algorithm, and this is the final result. We also designed a non-adiabatic taper. So we went from a small waveguide in a very short distance to a large waveguide cross-section. As you can see, because it's short, if you just increase the waveguide width linearly, you end up getting multi-mode, and you actually, if you look in this background, there's a lot of fields radiating and you have leakage. Here, we told the optimization algorithm that we want to keep it in the fundamental mode, and we want it to be as efficient as possible. And so this ended up being like 99.9% efficient. As you can see, there's some weird multi-mode stuff going here as the spline curve pinches and expands the field. However, once you get to the end, you've got straight vertical bars, which indicate that it's all in the fundamental mode. So this was a waveguide taper structure that we optimized. And so now I would like to conclude the talk by briefly touching on our latest work, which is going into 3 dimensions. So these were 2-dimensional approximations. So these were using effective index methods and so on and so forth, but we used 2-dimensional simulation techniques. And so the real world that we live in is a 3-dimensional world. You don't have a flat house, you have a 3-dimensional house you're building. This splitter here is not infinite into the page. It actually has a finite width, which is sub-wavelength. It's fairly small. This taper, same thing. It's not infinitely long into the page as a two-dimensional simulation would be simulating. It actually has a small finite width. And so in order to get accurate simulation results and to get consistent performance between running your optimization and designing a device and then fabricating your device and expecting your simulations to coincide with your measurements, you need to actually, or you should be actually doing everything in 3D and optimizing, simulating everything and modeling it in 3D and using that for your optimization algorithms. Of course, 3D is a lot more challenging than 2D and ends up being considerably slower no matter how you slice the cake. So our goals are to come up with methods to make it as efficient and as accurate as possible. And so we have and this is based on a recent paper that we have under review. Actually, it's the first version of it is available on arXiv if you are interested and you want to take a closer look at the mathematics involved behind it. In order to come up, we want to come up with a high order accurate 3D surface integral method. So in the same way, we want to preserve as many of the nice properties of the 2D method in the 3D method. And so in order to do that, we need to choose a geometric representation. How are we going to mesh our structure? We need to choose a discretization approach. Typically, the two most common ones are Nystrom or Galerkin. Galerkin is also often referred to as method of moments. We need to come up with an approach to represent the surface densities, the unknowns. And we need to come up with an approach to deal with the integrals. Integral equations, the most challenging part is dealing with computing these integrals accurately. And the reason why these numerical integrals can be tough to treat numerically is because they have singularities that are involved, and you have to be careful with how you treat them. And if you just use a standard method of numerical quadrature, you're going to get very little to no accuracy. And so we need to deal with far interactions between sources and targets that are far away from each other in a certain way. And we need to deal with the self interactions which have singularities and the close interactions which are not singular but are near singular because they're close to the source itself in a different way. And so for the geometric representation, in order to be able to be as expressive as possible while needing to use the fewest number of unknowns, we opt to use a curvilinear quadrilateral parametric patch as our sort of building block element to represent any arbitrary complex surface. And so this allows us for all of our integrals to integrate from -1 to 1 in the UV space. And then using a parametric mapping, we can map it into any arbitrarily curvilinear parametric patch. And so this gives a lot of flexibility. And for example, we can perfectly represent a sphere using 6 patches or any other sort of curvature. And typically people use triangles or they use flat representations. And that requires a very large number of these triangles in order to represent curvature, which increases your number of knowns by quite a bit. And so this is why it's advantageous to use a curvilinear parametric representation. So for a surface density representation, we want to have a higher order method. So instead of just using linear basis functions, which is typically what most people for method of moments do, and there are, if there are any method of moments practitioners here, I'm going to say this as a disclaimer so that you don't get upset with me. There are high order method of moment approaches and that use typically Legendre polynomial representations. But the most typical method of moment representations, the most bread and butter implementation uses RWG functions to represent the unknowns, which are linear basis functions. And conversely, because of the fact that you have linear basis functions, you end up getting a low order accuracy. You get a first or second order accuracy at best, essentially. And so because we want high order accuracy, we want to essentially get spectral accuracy, or as close to spectral as possible with respect to the number of unknowns or the fineness of our mesh. We choose to use a Chebyshev polynomial representation to discretize our unknowns on each patch. So on each unit grid here, we have a 2D grid of unknowns. And because we are using Chebyshev polynomials to represent them, that means that our unknowns are on a non-uniform grid, which isn't really a big deal because it doesn't matter within this patch where you put your unknowns. So it just means that they're non-uniformly spaced within this patch. And this allows us, the primary reason that we're doing this is that it enables us to use very accurate integration methods to handle the far and the near integrals using the Nystrom method. And the integration strategy, and I'm glossing over a lot of details and I'm simplifying things quite a bit because it ends up getting pretty involved, and I just simply don't have enough time in this talk to do that. But if you are curious, I would highly urge you to look at the preprint of the paper that I listed earlier on the slide, or to contact me and ask me about it. And the far integrals can be treated by using Clenshaw-Curtis quadrature. And so Clenshaw-Curtis quadrature is a high order quadrature method. It is similar to Gaussian quadrature in the sense that it's in theory not as accurate as Gaussian quadrature. However, in practice, for many types of functions, it is as accurate. And it allows you to essentially get spectral accuracy for smooth integrands. And so what it essentially does is it approximates the integrand using a set of Chebyshev polynomials, and then those polynomials get integrated exactly because you have them in closed form, and then that's how you compute the result of the integral. The other way to think about it is that it is change of variables, which makes the function periodic, and then you use trapezoid rule, and it is well known that trapezoid rule has spectral convergence on periodic functions. The other advantage for Clenshaw-Curtis quadrature is that it's quite easy to compute the integration weights. So you can just compute them using either partial summation if you have a small number of weights, or fast Fourier transforms if you have a large number of weights. And for the singular integrals, we can use a UV to ST. So we can use a change of variables which maps the unit square back to the unit square, but which introduces a Jacobian that vanishes at the same rate that the denominator vanishes, that's singular, at the point where it vanishes, and cancels that singularity. So this trick allows us to essentially handle the singularity with a change of variables. And because we're representing the unknowns on each surface patch using Chebyshev polynomials, we can pre-compute the Green's functions kernels, the integrals, against each of the Chebyshev polynomials, and ahead of time, before we do the simulation or the solve or anything. And then this gives us numerically the quadrature weights that we can use for the singular integrals. So it allows us to pre-compute a lot of information for the singular integrals that normally would be very expensive to compute. So it allows us to do this quite efficiently. And so enough with all of the low-level details. I want to sort of show you some of the results that we've gotten. And so I have a convergence study on the left. This is the error in the far field. On the x-axis, we have the number of unknowns. On the y-axis, we have the error compared to an analytical solution. For the cube, it's not an analytical solution because there isn't one readily available, but we used a trick where we put the source, it's a PEC or perfect metallic cube, and we put the source inside the cube. And so we know analytically what the surface densities need to be, because the resulting far field needs to be 0. If you put a source inside a metal box, no field should escape from it. And so if any fields do escape, it's because you have inaccuracy in your simulation. So that's how we can compute the accuracy or the error in the far field for the cube case. So as you can see, we have a 12th order slope that we've drawn here in terms of the number of unknowns with respect to the error. And then on this comparison here, we have a method of moments method using a commercial solver. So you can see that's just the first order slope, and our approach needs considerably fewer unknowns, primarily because it's using curvilinear patches rather than flat triangular representations, but then also converges much, much quicker as you increase the number of unknowns. And here we have the surface electric currents on the circle, on the cube, and this is the difference between the surface electric currents in the near field and the electric currents from a Mies series expansion. We've also implemented dielectric case, discretizing the N-Mueller formulation. I didn't mention this was the magnetic field integral equation that we were discretizing here. Dielectric case, we see similar results. We see we have a 14th order slope. We actually get a slightly higher roll-off in the slope here, drop-off. And so this is a 2 lambda sphere where the internal dielectric constant is 2, and the external is free space. It's just 1. So the method of moments for the cube and the sphere, you see here, there's still only first order. For the sphere, we actually have, here we're comparing it against the fourth order slope. Now the cube is interesting because for the cube case for dielectric, we can't use the same approach where we put a source inside, and so we need to irradiate with a plane wave. And so we need to compare against a very finely discretized solution so we discretize much more finely, and we use that as our ground truth. And as you can see, if we don't do anything special, you kind of get just a first order slope again. It's still actually a lot better than the method of moments because you still need considerably fewer unknowns to get lower error. So that's good, but you can see that the error is decreasing very gradually. And the reason for this is that a cube does not have smooth densities at the edges and corners. It has singularities, and for the dielectric case especially, the gradient of the densities blow up and are singular. And so in order to accurately represent that with our unknowns, we need to do an edge refinement in terms of how we space our unknowns on each of the patches of the cube. And so if we do that refinement, we can see that we recover the performance again, the similar slope as if we had a smooth surface like a sphere. So here we're just showing the radar cross sections compared to exact me-series solutions. You can see that the results from our solver are exactly on top of the analytical solutions. This is again for a plane wave incident from the -z direction. And then just to show you that we can do more complicated things than just scattering from simple canonical objects like cubes and spheres, we imported some 3D models from CAD software, and we scattered, again, from plane wave from the -z direction from them as well. And so these are the surface fields. These are PEC objects, so they're metallic, perfect metallic objects, and we scattered from them, and these are the surface densities that resulted. As you can see from this bunny model, the ears have hotspots, and any sort of the elbows have hotspots because they're sharp corners. And so when you have sharp metallic objects, typically you have singularities or hotspots in the fields. And these are the radar cross sections in the far field from scattering from that plane wave. As you can see, they're significantly more complicated because there's all these different curves and pointy objects and different things that the plane wave can scatter from. And because we definitely do not have any sort of analytical solutions from these CAD objects for the far field, what we did in order to check the accuracy is we just discretized it more accurately, and we plotted the two on top of each other. So this is with n equals 12, so 12 by 12 Chebyshev polynomials per patch versus 10 by 10. This is also 10 by 10 versus 12 by 12. And you can see that they fall right on top of each other. So this kind of like concludes the talk. This is the future vision for our computational research, is we really want to completely solve the electromagnetic synthesis problem. So we want to come up with a sort of automated, completely automated approach that you can specify a design region, you can specify your parameters. Maybe you're trying to design an antenna, maybe you're trying to design a nanophotonic device like a grating coupler, any sort of device. You can specify your objective function, you can specify computational constraints, fabrication constraints, input, output ports, and then the computer algorithm works really hard, and it gives you a result that matches the desired performance as close as possible, has robustness metrics built in, and you could go ahead and fabricate this device and it works as expected. So this is kind of our long-term vision for where all of this, we would like to see all of this go. So in conclusion, hopefully I've somewhat convinced you that computation can be leveraged to automatically design many different kinds of devices across many applications throughout the whole electromagnetic spectrum, and that improving computational methods, so solving Maxwell's equations, and coming up with better techniques and faster techniques to solve them accurately is crucial for making inverse design or using optimization feasible and making it practical. And so I wanted to also highlight my group members because most of this, all of this work would not have been possible without them. And so my group is kind of split half and half between students who do computational work right now and students who do more integrated circuit design work. And so I want to conclude the talk with that and open to questions. I know I'm running quite late, and I wanted to thank you all for your time. I really appreciate it.
Great. Thank you very much, Professor Sideris, and for the great talk and devoted time. We don't have too much question. There was one question earlier in the talk that was about the scale of the size scale of the plastic waveguide, which I think you already mentioned that it's about a penny size, but
can you, because I can't see the chat, can you read what the question said, or let me?
The question is, what size scale do plastic waveguide work
what
on?
Size scale do plastic waveguides work? Is Patrick still in the? I guess he might not still be in the talk,
yeah,
but
anyway.
So typically the size of the cross section is on the order of about half wavelength or so. So and it depends on the material. Typically the dielectrics that are used are between like 2 to 5 epsilon. And so you can kind of do the math. Basically it ends up being, if you're around 100 gigahertz range, it ends up being around 1 millimeter or so in the cross section. I'm not sure if that's what he was asking because the question was a little bit ambiguous, but hopefully that was it. Does anybody else have any other questions? I would be happy to answer anything.
I have a quick question. On slide 27, when you were discussing the loss, so you were saying like if you don't use the plastic, there was like a difference between simulation and measurement. I couldn't quite understand what is the measurement.
Oh yeah, so this curve, which is more efficient, was if we took the simulation and we replaced the parameters of the real parameters of the plastic that we 3D printed with a lossless piece of plastic, so an ideal plastic. And so what I meant was that this implies that if we had used a plastic with lower loss, that we could have our results would have been better essentially. So it's not that our coupler wasn't very good, it's that the plastic that we had available was pretty lossy.
I see.
Someone asked a question in the chat, how would you suggest a beginner to get started with inverse design space tools? So that is a great question. There are some open source tools available. They typically use finite difference methods. So there's some tools, there's spins from Professor Yelena Vukovic's group at Stanford. There's EM-opt, and that was from, I think it's from Andrew Michaels, who was a graduate student and professor at Eli Yablanovic's group. And so those are 2 open source packages. Also, Lumerical has an inverse design package available these days. So if you have a license for Lumerical, you can use that. Otherwise, you can check out one of those free tools. We are intending, as we develop things, to release them as open source as well on our GitHub. So you should definitely be looking out for that. And so our goal is to not just develop tools that can lead to high performance designs and high performance structures, but to develop tools that can give back to the community and that can be used by the broader community and employed in their design processes. So that might take a little while longer from now because we're very actively involved in the process right now of developing the said tools, but we do fully intend to release these tools as open source once we get to that point. So somebody asked about open source tools for Fdtd. So the best open source tool that I'm aware of for Fdtd is called MEEP, M-E-E-P. And so if you just Google like MEEP Fdtd, the first link will be the link to that. And you can download it, it's open source. You can script it in Python, and it's can simulate many different things.
All right, great. I think with that, we conclude tonight's talk. Thanks very much again, everybody, for attending the talk. And also thank you very much, Professor Sideris, for the time. And that was a great talk. So we will announce the future talk information throughout the department and also on LinkedIn. Please consider following us on LinkedIn to keep to be posted about the future talk. Thank you very much.
Thank you for having me.
Thank you so much, Professor.
I appreciate it. Thank you for having me.
Thank you,
Bye.
Professor.